Hello everyone, this is Dilip Chakravarti, Assistant Professor in Cybersecurity Department, IAR Engineering College, Hyderabad. Today we are going to discuss about graphs, graph traversals. So in the earlier classes we have seen the definition of graphs and types of graphs. Then representation of graphs. We have seen different types of representation. Today's session we discuss about traversal techniques in graph. Actually, what do you mean by traversal? We all know traversal is nothing but visiting the node. Okay, visiting the nodes or visiting the vertex. Graph traversal means how you are visiting each and every vertex in the graph. So, are we maintaining some order? Okay, so we'll see all those things. Before going to see about that, we'll see the basic thing, basic definition of graph. Graph is defined as an ordered pair of set of vertices. It consists of some set of vertices and some set of edges. So we are representing it as G equal to V comma E, where V is some set of vertices and E is some set of edges. Okay, if we observe this graph, uh, it consists of five vertices A, B, C, D, E, and the edges are A, B, A, C, C, B, D, C, D, and D. Okay, these are undirected graph. We don't have any directions. We say it as undirected graph. Okay, and let's see about graph traversal. So, graph traversal is a technique used for searching a vertex in a graph. Okay, you are visiting each and every vertex in the graph. Why you are visiting it? You are searching for some vertex or searching for some node. Okay, a graph traversal is also used to decide the order of vertices is visited in the search process. How you have visited. So whether you are visiting this node first or that node first, which one you are going to visit. Okay, so we'll see. We'll traverse. We'll see those things. The graph traversal finds the edges to be used in search process. We are going to find the edges without creating loops. We are finding the edges. Okay, that means using graph traversal, we visit all the vertices of a graph without getting into looping. Okay, we don't get any loops there. There are two graph traversal techniques, and they are as follows. So it may be depth first search graph traversal technique or breadth first search graph traversal technique. Okay, so I can use any one of these techniques. We'll see what is depth first search and what is breadth first search. Okay, in smaller terms, we can say it as BFS and DFS. Generally, we use this terminology DFS and DFS. BFS, a traversal of a graph, produces a spanning tree as a final result. We will see what do you mean by spanning tree in the next session. So it produces this BFS produces the spanning tree. Spanning tree is a graph without loops. We don't have any loops in the spanning. We use Q data structure for breadth first search. So for breadth first search, we are going to use the Q data structure with a maximum size of total number of vertices in the graph to implement BFS traversal. Okay. BFS traversal of a graph produces a spanning tree as a final result. We have seen these things as I already told you. We are going to use Q data structures for implementing the breadth first search. Okay, the algorithm. What are the set of steps? What are the sequence of steps we are following in breadth first search? So first step, define a queue of size total number of vertices in the graph. Okay, so suppose if the graph consists of 5 vertices, the queue size should be 5. Okay, if the graph consists of 10 vertices, we will say the queue size is 10. We are going to define that queue size with the total number of vertices in the graph. And second, select any vertex. I am selecting any vertex as a starting point for my traversal. Okay, I may consider any vertex. Okay, visit that vertex and insert into the queue. So I may consider any vertex in the graph as my starting vertex, and I'm just inserting it into the queue. and visit all non-visitor adjacent vertices of what is vertex which is at front of the queue and insert them into the queue. Okay, so I am going to visit all the adjacent vertices of that initial vertex, whatever I have taken. Okay, so I'm just placing it in the queue. Okay, where there is no new vertex is visited from the vertex. So if there are no more vertex to visit, which is at front of the queue, then delete that vertex. We are going to delete that vertex. Okay. So we'll repeat these steps, third vertex and fourth vertex. So we are adding the adjacent vertices, and if there are no more vertices are there, we are removing it from the. Okay, we will see with an example. We'll get a clear idea about that. When queue becomes empty, then produce final span. So finally, we are going to get the final spanning tree by removing the unused edges from the base. Okay. So let's see with an example. Consider the following example to perform BFS graph. This is the graph here. We have taken how many vertices are there? 1, 2, 3, 4, 5, 6, 7. 7 vertices, and we will consider the queue size as 7. Okay, observe here. 1, 2, 3, 4, 5, 6, 7. I'm considering the queue with maximum size as the number of vertices, that is 7. Okay, so select the vertex A. So I can select any vertex, but here randomly I'm selecting first vertex as my A as my starting vertex. So I'm just adding that A to my queue. Okay, insert A into queue. Is that clear? I can consider any vertex. Okay, then step 2, visit all adjacent vertices of A. So as we have seen in the algorithm, so we need to visit all adjacent vertices of A. So I can the adjacent vertices of A are the neighboring nodes of A are B, E, and D. As they are connected, we say them as adjacent or neighboring vertices. Okay, we can add these vertices in the queue which are not visited. So D, B, E. So D, B, E. I can take it in any order. Don't think that we should take only in this order. So I can take any order. D, E, B. I have taken D, E, B. I just removed my A from Q. Okay, as I have adding my adjacent nodes of A, I'm just removing my A now. Okay, so A is removed and the children of A or the adjacent nodes of A are added to the queue. Now again the step 2 is repeated. I'll remove D and the adjacent of D are. What is the adjacent of D? A and E. A which is already visited and E which is already there in the queue. Okay, I just no need to add any more. So it is simply EB. Okay, so then visit all the vertices of F, E. So for E, the vertices are B, C, F. I'll remove E. Already B is there, so I need to add C and F. Okay, so I'm adding at the end. As you all know, insertion takes place at rear end, back end, and deletion takes place at front end. Okay, first I have removed A, then I have removed D, then I have removed E. Okay, then again I have to remove B. Okay, so B is removed and the adjacent of B. So A, C, E already completed A, C, E. Okay, so nothing is to be added here. So I simply remove my B. Okay, there is no vertex. I simply remove my B. Next, I am going to find the adjacent vertices of C. Okay, the adjacent vertices of C are F and G. Okay, so in the in this queue, observe here, we have removed C and then F is already there. So I need to add only a G. I'll be adding G. So next step, I'm going to remove F. The adjacent of F are E, C, G. Okay, E, C already visited. So finally it is G. Okay, so then finally I'm going to delete G also. So now all the vertices are visited. So I'm using this method, we call it as breadth first. So Q became empty now. So stop the BFS process. We are going to stop the BFS process. Final result of BFS is a spanning tree, as I already told you. So the thing is, we have only these things: uh, A, B, D, E, C, F, G, D something. Okay. So we got the path like this: A, D, A, B, A, E. From E, then C, then from E, then F, then C, G. Okay. Uh, so this is about breadth first search, where we are considering Q as my data structure. Now let's see about depth first search. Okay, here we are going to consider the depth first data structure as stack. Okay, we'll be considering the data structure stack and we'll be implementing depth first. Okay, so DFS towers of graph produces a spanning tree as a final result. Here also we are going to produce a spanning tree. Spanning tree is a graph without loops. We all know that spanning tree is a graph without loops. Okay, who is the stack data structure with the maximum size of total number of vertices in the graph. How much size we have to consider for stack? As the number of edges, whatever the number of edges, whatever the number of vertices that are there in the graph, so we'll be considering that many number of that is the size of our stack. Okay, we'll implement it with a diagrammatical representation so that you will get a clear idea about that. So before that, let's see the algorithm for depth first search. Okay, so first define a stack of size. So I need to define the stack size with total number of vertices in the graph. Okay, if my graph consists of 5 vertices and the stack of size will be 5. Okay, select any vertex as a starting point for graph. I'm going to consider any vertex as my starting point. Visit that vertex and push it onto the stack. So you will be considering any vertex of the graph as your starting node, and you should push it onto the stack. Okay. So third step, visit any one of the non-visitor adjacent vertices of A. So whatever the vertex you have pushed onto the stack, you pop it. Okay, you pop it, and what you need to do is you need to push the adjacent vertices of that popped vertex. Okay, you need to push the adjacent vertex of the popped vertex. Visit any one of the non-visited adjacent vertex of vertex which is at the top of the stack and push it onto the stack. Okay, I'll be repeating this step 3 until stack becomes empty. Okay, so when there is no new vertex to visit, then use backtracking. If there are no new vertices to be added to the stack, then we'll just backtrack it and we'll pop one vertex from the stack. So after completion of my step 4, so there are no vertex to be visited. Okay, all vertex are already visited. Okay, maybe some are there in the stack. Okay, if there are no more vertices to be added, we'll just pop the vertex from the stack and we'll proceed the we'll repeat that procedure. Okay, we are repeating steps these 3, 4, 5, adding the adjacent vertices, and until a new node found, we are going to add it. If no visitor nodes are there, if no new nodes are there, we are popping the element from the stack. Okay, we'll get a clear idea when you see a diagram. So it may be little bit confusion when you talk when you talk the theory like this. Okay, so when stack becomes empty, then produce final span. I'm going to get a final spanning tree. Backtracking is coming back to the vertex. We are just coming back to the vertex from which we reached the current. Okay. Consider the following graph. So for this graph, for the same graph, whatever we have seen for breadth first search, I will be considering the same graph for depth first search. Here we are considering 7 vertices, and the stack size should be 7. Okay. Observe here the stack size is 7. 1, 2, 3, 4, 5, 6, 7. So now, according to algorithm, second step is visit any vertex. I'm going to visit any vertex, and I am going to push that vertex onto the stack. So here I'm starting A as my vertex starting point. I'm pushing A onto the stack. Okay. So then visit any adjacent vertex of A. So the adjacent vertex of A are B, D, and E. I can visit any vertex. I'm just adding that vertex to the stack. Okay, I'll be adding that vertex to the stack. So we need visit any adjacent vertex of B again. So I'm going to visit the adjacent vertex of B. I'm just adding it to the stack C. So then from C, I'm going to visit to E. I'm taking it as E. Okay. From E, so I'm going to visit my adjacent vertices, either D or F. Here I'm going to consider it as a D. Okay. So then there is no, after reaching D, there is no vertex to visit. So there is no vertex. Already I have visited A and E. So what I need to do is I need to go back. Okay, from where I started. So I went to E. So again from E I am checking. So whether all adjacents are completed. Yeah, here all are completed except F. So what I will do, I'll just add my F. Okay. So visit an adjacent vertex of E, which is not visited. I'm just adding it as adding that vertex to my stack. Okay. So then for EF, I'm just adding C, sorry, G, last one. Okay. So then remove each node from the stack. So as there are no more nodes to visit, I need to backtrack. So I need to backtrack and I'll go. So still I don't found any new node. Okay. So I'll be removing my Z. I'm popping Z, then I'm popping F, then I'm popping E, then I'm popping C, okay, then B, then A, B, then A, okay. So finally my stack becomes empty, okay. So in this way I'm going to traverse, I'm going to traverse by using stack depth first. I hope it is clear. So what we are doing is we are just visiting a node which is not visited. I'm just adding that to the stack. From there again I'm visiting any node which is not visited. If all visited nodes are completed, so I'm just going backtrack. I'm just going to back and again I'm seeing there whether it has any adjacent nodes which are not visited. If not visited, I'm adding to the stack. Okay. So this step is repeated until I complete all the nodes. Okay. So I'll be completely finishing my stack. I am making my stack as empty. This is about depth first search. I hope it is clear. Still, if you are having any doubts, you just go to the example or we'll just see the explanation. Okay. Thank you.